Hello everyone, my name is Andi Zaky Ashari, and now I will giving some brief explanation about the architecture that I have created. So in this video, I have created a transformer architecture for predicting the stock price. The company that I use for predicting the stock price is the AMD company, which is a advanced micro devices company. And now we are headed to the data understanding section. This first section, I want to see the average closing price per year for AMD company. So I transform the date into the date time and then extract the year from the date variables to assign it to a year column, and then grouping the data based on the year variables. And as we can see here from the plot, this dataset spans from 1980 to 2020, which explains that the AMD first went public on 1980. As we can see here, from 1980 to 2015, the stock price for the AMD company relatively fluctuative until the 2015 the stock prices is quite rocketing until reach the 50 US per paper. And the next section for data understanding, I will print the data information and the first couple of lines for this data sets and the descriptive statistic for the dataset. The dataset information here we can see that these datasets contain 8 columns, which is 1 column for date time, 5 for float or decimal, and 2 for integer. This dataset has no missing value. And now we are headed to the first couple of lines for this dataset. We can see the first 5 lines here. We can see the first 5 data for date, open, high, low, close, adjusted, close, volume, and year. You can see here on the descriptive statistic section, this shows that the mean closing for the close variable is approximately around 11.21 USD with a standard deviation approximately around 8.28. And since this dataset spans from 1980 to 2020, making it suitable for our predictive models. And we are headed to the pre-processing and data splitting section, where in this first section we can see that I change the date into an index since we are working on a time series dataset. And then the second thing I do here, I normalize the data using min-max scaler. And min-max scaler is used to scale the closed columns for the datasets, so making it suitable for modeling. And then I set the window size and the horizon according to the exam requirement, which is 5 for window size or output and 5 for horizon or out. And now we are headed to the splitting the time series dataset. Here I made a function called split sequence. This function is defined to split the time series data into input sequence of x and corresponding output sequence of y, and then it will iterate the sequence creating the x and y pairs based on the window size and the horizon. And the input sequence of x consists of a sliding window of a length window size, and the output sequence of y consists of the values following the window. And now separating the data here on the and now the separating data section. And now here on the separating data section, this function will be called with the close values and the window size and the horizon as its parameters. And now here we are splitting the datasets into 80% of training, 10% of validating, and 10% for test. And as we can see here, I have printed the shape of X train, Y train, and X validation and Y validation so that I can see the number of samples and the number of time steps in the input sequence. And now heading to the modeling section. First thing I do here, creating the baseline architecture. But before creating the baseline architecture, I made a class called positional encoding. It is a custom positional encoding, and it inherits from the Keras layer, and it inherits from the Keras layer class, and is used to add positional encoding to the input sequence. In this class, I define a function called get angles. This will calculate the angles from the positional encoding based on the position of index and the model of depth. These angles are used to create the positional encoding for each position in the sequence. And I also define a function called call. This is a method of the positional encoding layers. Takes the input and the compute to the positional encoding, and then it will calculate the sequence of length and depth of the inputs, and will generate the angles using the getAngles function, and then applies the sine and cosine function to alternate angles, and they add positional encoding to get the input. And then we are headed to creating the first transformer model, which is the baseline model. This function will takes a input shape and the output shape, and also the number of blocks as the input parameters. Inside the function, an input is created with a specific number of input shape. The input shape will be the window size and the output shape will be the horizon. And then the input sequence is passed through a dense layer with 64 units and a dropout layer with a dropout rate of 0.2. And then we will head it to the positional encoding embedding, where this section will call the positional encoding that we already made before, and we will head it to the next part. The specified number of transformer blocks are created using a looping. For each block consists of a multi-head tension layers, followed by a normalization layers and a feed-forward network that will contain a convolutional layers, addition, and a layer normalization. And finally, on the last layer, which is a linear layer with the specified output shape is applied, and the output is reshaped by taking the mean along the time axis of one. This model will be created using the input and output layers, and the model is compiled with the Adam optimizer and the mean squared error. This first baseline architecture will be trained with 10 epoch and the batch size of 64. As we can see here, from the epoch 1 to epoch 10, the validation load relatively very low, and we are headed to the performance for this first baseline architecture. After the model is trained, we are now make the prediction on the test dataset using the trained model with using X test as its parameters, and we are calculating the RMSE, the MAE, and MAPE, and R2 to see our architecture performance. As we can see here, the evaluation metrics are already printed. This section provide a summary model performance, and in this case, the RMSE, we got the value of 1.95, the MAE of 1.52, the MAPE 11.24%, and the R2 score of 97%. This indicates a very good performance. But let's try to create a modified architecture to get the best performance that I could get. Okay, on this first modified architecture, I have made the copy of the previous function called create transformer model, but I add the modified for its name. And this function will take a bunch of parameters, including the input shape, the output shape, the default number of num-block, the default number of depth units, and convolutional units. This all a default number, which I can change when I want to create the modified models. On these models, I increase the dropout rate to 0.5, and also the blocks to 6, the dense unit to 256, and convolutional units to 128. These models also compiled using Adam optimizer, and for the loss function using MSE. And for the epoch, I increase it into 800, and the batch size also increased to 128. As we can see here, from epoch 1 to epoch 800, the validation loss is also small, but not as small as the baseline. And let's head it to the model performance of the first modified architecture. As we can see here, we got a higher RMSE, higher MAE, higher MAPE, and a very low of R2 score. When we compare this first line model to the baseline model, the baseline model has lower RMSE, which is 1.9, and the first model is 14.5, which is very high. And also the baseline got the MAE of 1.5, and the first modified got 10.02, which is very high too. And the MAPE for the baseline is 11.24%, and the MAPE got 51.2%, which is very big number too. And the R2 score for baseline, we got 0.77 or 77% and 97%. And the first modified model, we got minus 0.45, which is a very low of R2 score. And overall, the first modified baseline performed worse than the baseline architect in terms of accuracy and the capturing of variance in the data. So let's try to create another modified architecture. On this second modified architecture, I decreased the dropout rate to 0.2, the number of log I decreased into 2, the dense unit into 33, and the convolutional unit into 33. As like the other models, this model is compiled using Adam optimizer and loss function of MSE. This model is trained using 100 epoch and the batch size of 32. From epoch 1 to epoch 100, we can see that the validation loss is already decreased very significantly. So which is this model must be better than the first modified model. So let's see the performance. The second modified models perform better than both the first model than the baseline model. This model achieved a lower RMSE value of 2.64. The first modified, if we want to compare to the other model, the first modified model is 1.14.5 and the baseline model is 1.9. And for the second modified architecture, we got the MAE value of 1.4. If we compare to the first modified architecture, we got 10, and the baseline we got 1.5. And also the MAPE, we got a significantly lower MAPE for second modified architecture. We got 6.68%. When we compare to the first modified, we got the 51.2%, and the baseline we got 11.2%. And for the R2 score of the second modified architecture, we got a score of 95%. Compared to the first modified architecture, we got minus 0.5, and the baseline we got 97%. So the second modified architecture model demonstrate improvement in accuracy and the predicting capability compared to the previous model. But let's try to create the other modified models to see if we can get the better performance. On this third architecture, I increased the dropout to 0.4, the number of blocks into 3, the dense unit into 64, and the convolutional units into 64. And also, same as before, this model compiled using Adam optimizer and loss function of MSE. This model is trained with 150 epoch and the batch size of 64. We can see here that the validation loss is also relatively very small. So let's see the model performance. On this third modified model, these third models outperform all of the previously created models, which is the second modified, the first modified, and the baseline models. These models achieve a lowest value of RMSE of 2.1. If we want to compare to the previously model, the second modified, we got 2.6. The first modified, we got 14.5, and the baseline, we got 1.9. And these third models got the MAE value of 1.3, and compared to the other model, which is second modified, we got 1.4, the first modified we got 10.0, and the baseline we got 1.5. And for the MAPE, we got some comparable MAP of 6.86%. If we compare to the second modified, we got the 6.68%, and the first modified we got 51%, and the baseline we got 11.24%. And also for the R2 score of third modified, the architecture, we got a slightly higher R2 score. We got 96%. If you compare to the previous model, we got on the second modified, we got 95%. The first model we got minus 0.545. The baseline we got 97%. These third models demonstrate a very good performance and improved accuracy, and making it the best choice among the other models. But let's try again for the last time to see if we can get the best performance or best models. On this last model, I decreased the dropout rate into 0.3, and I decreased the number of logs into 3, and the dense units into 64, the convolutional units into 64, and I increased the batch size into 128. But in this model, I add the second convolutional layer. But the reason why I did this is so that this model can capture more complex pattern and features in the data. This model is trained with 150 epoch and the batch size of 128. Let's see the performance of this model. This first model exhibits the best performance among all of the previous models. If we see the performance, it achieved a lowest RMSE value of 1.62. If we compare to the previous model, which is the third model, we got 2.10. The second model we got 2.6, and the first model we got 14.5, and the baseline we got 1.9. And also we got the lowest MAE value of 1.04. If we see the previous model, on the third modified model we got 1.3, the second model we got 1.4, and the first modified we got 10, and the baseline we got 1.5. For MAP value, we got some comparable value of 6.0%. If we compare the previous model, the third modified model, we got 6.8%. The second modified, we got 6.6%. The first modified, we got 51.2%, and the baseline, we got 11.2%. But for the R2 score on the third modified architecture, we got the highest score of R2, which is we got 98%. If we compare to the previously model, the third modified model we got 96%. The second modified we got 95%. The first modified we got minus 0.45, and the first modified we got 51%, and the baseline we got 11.2%. Sorry, the baseline we got 0.97%. This fourth modified model demonstrates the best accuracy and predictive power, making it the top performing model between the previous model. Although the dropout value, the dense units, and the convolutional units are relatively smaller in this fourth model compared to the other models, it achieved a better performance due to the presence of this second layer of convolutional layer, where it allows this model to capture more complex pattern and the features in the data, leading to improved predicting capabilities. As I said before, these additional layers can capture more complex data, enhance predictive capabilities, and allow the model to learn, create representation, and exploit data relationships. The larger batch size is also contribute and improve the stability during the training. Thank you.